So in today's class we would be discussing about the substitution reactions. So as you can see that there are mainly two types of substitution reaction. One is substitution nucleophilic unimolecular reaction. We know it as SN1 reaction. Apart from that, there is another type of substitution reaction which is known as substitution nucleophilic bimolecular reaction, which is known as SN2 reaction. So they are the main two types of substitution reaction we experience during any type of reaction. So today we will start with SN2 mechanism. After that we would move on to the SN1 reaction. So in the first part you can see that there is an alkyl halide here, right? So which is a 1 degree alkyl halide, right? Because it is connected to a 1 degree carbon. Okay, so now if you just react it with OH minus, so basically you are putting it in an alkaline medium where KOH is there or NaOH is there. So what would happen is it would substitute this bromine and this OH would be coming here. So we would get alcohol, which is 1 degree alcohol. Now rate of this reaction depends upon the slowest step. So just think about it. If you are going to an expedition with your friends, okay, and you are just going there to a trekking. Now think about this situation that there are three of you and you are climbing a rock. Okay, now you all of you don't have the same rate of walking, so definitely you can see that A is a little bit ahead of B and C. So definitely A would reach faster if nothing happens. So A would reach here faster, reach to the cliff first. After that B would come and after that C would come. So you three are the team. Now think, when would we call that your team has reached the top? When C would be there, like A would be reaching there first, after that B would reach, after that C would reach there. So when C reaches the top, only then we can say that your journey is over. And now you can see that C is the slowest one. So for any type of journey, slowest step, the slowest one is the determining parameter of the end to the journey. So similarly, for every reaction as well, you can see the slowest step is the rate determining step, RDS. We call it RDS. So this slowest step is the only step that determines what would be the kinetic parameters of the reaction, what would be the speed of the reaction, or what would be the rate of the reaction, right? So this is known as RTS. Now here rate depends upon the concentration of both reactants. So first we need to know this thing, that note, which is rate of a reaction is always dependent on the reactant concentration. So this is a very good thing, like you need to understand this part, that rate of a reaction always depends on the concentration of the reactants. Why only the reactants? Because reactants are giving the amount of whatever it needs, whatever the reaction needs. The reactants are giving that thing. So think about it. If you have more amount of money, you would be able to spend more. If you have less amount of money, you would be able to spend less. That is the similar thing is happening here. So when the reactant concentration is high, the rate of the reaction would be high. When the reactant concentration is low, the rate of the reaction would be low. So we can say the rate of the reaction depends on the reactants, right? So now, as you can see, for this reaction, for this type of reaction, this is the only step. So you can see that there are two types of reactions are there. One is single step and another is multi-step reaction. So actually what happens is this is the single step. Okay, so this is the rate determining step because this is the single step. So when the team is for one, like only you are going to the expedition, then the rate would be depending on you only. You are the team. You yourself is the team, right? So similarly, for the same thing is happening here as well. So you would be able to see that the rate would be depending on both of the reaction because this is the only step happening in this reaction. Okay. So this is how the reaction happens. So from this mechanism you would be able to understand why we call it a bimolecular reaction. So as you can see, this is a nucleophile here. So this is nothing but the OH minus. And in this CBr bond, this is a polar molecule because there is some electronegativity difference in between the carbon and the bromine. So for that reason, carbon is getting delta positive ion and charge, and this is getting delta negative charge. Now, this OH minus would attack this carbon as it is having a delta plus charge, and what would happen is this Br minus would get out of the system. So, what would be the transition state of this reaction? What would be the intermediate state of this reaction? Definitely when both of them are getting attached here. Okay, there is no such real bond, there is a very weak interaction because I am trying to show that this bond is about to break and this bond is about to build, right? This is the intermediate part, and you can see in this state you can see this is overall, this is a one-step reaction. So you can see in all the steps that both OH minus and Br, both this OH minus and this molecule both are involved. So for that reason we can say this is a bimolecular reaction. So what would be the result of this transition state? So you can see after some time Br would get out from the reaction and it would be an inversion of configuration. So as you can see, what was the initial state when Br was in the right side. So now the product whatever is coming, OH is in the left side. So we call it an inversion of configuration, as you can see it here. So let's see what are the characteristics of this reaction. So they are saying that this reaction is a one-step reaction. So as I have told you earlier, because this is a one-step reaction, that was the reason why this is the bimolecular reaction as well. Apart from that, you can see there is an inversion of configuration. We have already seen this thing, and only best result for 1 degree halide. So you can see this is a 1 degree halide. I have taken the example of a 1 degree halide here and here as well. So why for 1 degree halide only? Why not 3 degree halides are susceptible towards this reaction? Look, sometimes there are some examples where 2 degree halides also undergo this type of mechanism, but definitely they have a lower rate. So we would discuss about that, why 2 degree and 3 degree are not that much susceptible towards this type of reaction mechanism, towards Sn2 substitution reaction. Now just keep that in mind that this is susceptible for SN1 type, for 1 degree alkyl halides only. Now the fourth thing is presence of a good leaving group is needed. So what are the criteria? One criteria is we need a 1 degree halide for the best reaction, for the best yield. We need a 1 degree halide, and the second thing is we need a good leaving group. We will discuss about this as well. What are the leaving group? How can we call a leaving group a good or a bad? Okay, we would look after this as well. And fifth point is always occurs via backside attack. As you can see, always occurs via backside attack. Okay, so now we would move on to the next part where we are going to discuss about the criteria. One is why we take 1 degree alkyl halide groups, and the second thing is why we need leaving group and what is leaving group and how can we call a leaving group good or bad. So you can see leaving group is considered as one of the most important criteria. So this is one of the most important criteria of Sn2 mechanism or Sn1 mechanism as well. Leaving group should be able to leave taking with it the electron pair. So the electron pair of CX bond. So I have seen you earlier. So here Br is the leaving group. It is going to leave this system. So this has to be a good leaving group. So what is a leaving group? Leaving group, that is something that takes up the 2 electrons of this bond. Okay. The relative ease at which it can be displaced is known as leaving group ability. So the less amount of pressure, less amount of effort you need to leave a leaving group is called an ability of leaving group. okay, which depends on the capacity to accommodate the negative charge. So as you can see, leaving groups is something that takes up the negative charge. So think about it. If CBr bond breaks, Br is going to take up the electrons of this bond. So Br is going to be Br minus. So Br is going to be Br minus, but if it cannot accommodate this minus charge, if it cannot stabilize this minus charge, then this thing would not be stable. So Br would not get out of the system. So a good leaving group needs to know how to accommodate this minus charge. He needs to know how to make this situation stable. Otherwise, this is not a good leaving group. So which depends on the capacity to accommodate the negative charge. So for halogen, as you can see, that I minus has a very big size. So the minus charge can like spread itself, can what we call it is can dissolve itself, right? So throughout the area, so it is getting a higher area to disperse or diffused or get delocalized. So that for that reason, I minus is a very good leaving group. Apart from that, after that Br minus comes, because Br minus has a smaller size, so the ability to accommodate this minus charge is less than I minus. Thus it goes to Cl minus and F minus. Okay, so I think you are okay with this. After that, we are going to the reactivity of alkyl halides. So why we have discussed that 1 degree alkyl halide is only susceptible towards this type of reaction. So they are saying that CH3X after is the most susceptible alkyl halide. After that, we have to go for 1 degree halide. After that, 2 degree and 3 degree is the least susceptible towards this type of reaction. So why is this happening? We call it a steric effect. Steric effect is nothing but the crowding effect. Okay, so as you can see, nucleophile is going to attack this carbon here from the back side, right, to make this X out of the system. So how would it be able to attack? If this is a 3 degree alkyl halide, so you can see that this carbon is getting attached to 3 CH3 groups. So you can see that 3 CH3 groups can take up some space. So if it happens like this, how would nucleophile be able to attack from the back side? Because there is no such space from where nucleophile can enter. So it would not be able to enter from the back side. So this type of reaction would not happen. This we call a steric effect or steric crowding effect. So now we will discuss about the SN1 reaction. So as you can see, 1 is denoting us that this is a unimolecular reaction. Means in the RDS, the rate would be depending only upon the concentration of any one of them. We would go to that. We would come to that. So what would happen is, if you just, as you can see that for 1 degree radical, it undergoes SN2 reaction. Then what is for 3 degree radical? What happens for 3 degree radicals? So for 3 degree radicals, you will be able to see that it undergoes, it gives our expected products, but via a different type of mechanism. So let's go to the rate expression. So you can see the rate expression. In the rate expression, it is dependent only upon the concentration of this thing. So why is this happening? So let's just go into the reaction pathway. So as you can see in the step 1, what happens is, first, this Br being a good leaving group, as you know, what happens is it goes out of the system first. Okay, why? Because if it goes out of the systems, Br minus is a stable thing, right? As you have read in leaving group, that Br minus is a very good stable leaving group because it can accommodate this minus charge. And if it leaves, it would give us a carbocation which is also stable, because this is a 3 degree carbocation. So due to the plus I effect of 3 methyl group, this carbocation is also stable. So for that reason, this bromine being a stable leaving group, and due to the formation of a stable intermediate, the bromine leaves the system first. So in the SN2 mechanism, there was someone who was hitting from the back side to make it leave, but from this mechanism, no one is needed. It would leave on its own. So this step is slower. As you can see, a stable configuration is getting broken. So for that reason, this step is slower. So as you can see, if this is the slower step, so definitely the rate of the reaction would be depending on this step only. Now tell me, in this reaction, which one is the reactant? This is the reactant. So that for that reason, the rate is depending on this thing only. Okay, so for that reason, we call it a unimolecular reaction. Now what is the step 2? What happens next? Now you can see after that what happens is there is OH minus in the solution. So this minus gets attached with this carbocation to give us a product, which is a fast step, because as you know that due to this the formation of the OH minus, the addition of OH minus is very much fast, because that is there are some ion pairs in it. Well, one more thing is needed to discuss. Such type of reactions are carried out in a polar protic solvent like water, alcohol, etc. So why in polar solvent? Look, if you want, you can see that this step is a reversible step, right? So this can convert into this product, and it can also get reversed back to this part. So, but we need this intermediate to get our product, right? So we don't need that, we don't like that our product get converted into the reactant. So we don't want this back step happen. So for that reason, we are using polar solvent. So what would be the need of this polar solvent? The polar solvent, as the solvent is also polar and this thing is also polar, so solvent would stabilize this thing. So what would happen is this would get stabilized by the solvent, as the solvent is polar due to the dipole-dipole interaction. So what would happen is this step would get this would get a further stabilization. So this process would be unidirectional. Okay. So as we are stabilizing this part, so this reaction would proceed further. So we would get our product, right? So after that, like I have written it here, if we use polar protic solvent, it would stabilize the carbocation, right? Okay. But sometimes what happens is, sometimes we get some product which we haven't expected. Sometimes we get some unexpected products as well. So I would show you some example of that. Due to this happens only in SN1 type of mechanism. So why is this happening? I would show you a reaction where this is the reaction where you will be able to see that if this is our reactant, so what product do you expect? You expect this Br would get substituted with OH. Okay, you expect this thing, but in this reaction, this is the major product. So why is this happening? How is this happening? So for that reason, you need to know rearrangement. So what is rearrangement? Rearrangement is something like the molecules itself changes itself into a certain thing that is more stable than the previous one. I'll show you. Look, there are mainly two types of rearrangement. One is hydrogen shift, one is methyl shift. First, let's discuss about the hydrogen shifting part. So, carbocation is an intermediate for SN1 reaction, right? Which undergoes certain rearrangement to be stable. So, carbocation to get further stabilization undergoes some rearrangement as well, which gives us unexpected products sometimes. So let's see what happens. So whenever you just react this thing with OH minus, it undergoes some SN1 mechanism to give us this product as the major. As you can see, this is something unexpected. We expect this thing, but this thing is the minor product, right? This is a minor product. So why is this happening? So for that reason, we have to see our mechanism. So this is our mechanism. So as you can see, when first what would happen, this Br would get out of the system, right? So a carbocation would form. Now look at this. This is a 2-degree carbocation. As you can see, 2 carbons are attached to it. But if one hydrogen gets away from here, one hydrogen gets shifted from here to this carbocation, then what would happen? Then definitely this carbocation would get formed, right? This hydrogen is getting shifted. Why? Because then it would form a 3-degree carbocation, as you can see. So rearrangement via hydrogen shift is happening here. So this carbocation being more stable than 2 degree, we expect this thing to happen. After that OH minus reacts with it and OH minus comes and get attached with it. So that's how we get this type of products. We call it 1,2 hydride shift because this one is 1, this is 2, and 2 to 1 a hydride shift is happening. So that's why we call it a 1,2 hydride shift. Okay. Now the next thing is, the next type of rearrangement is methyl rearrangement. Okay. Now you can see that methyl shift. Okay. So how is it happening? So if we take this type of a reactant and if it reacts with bromine, then similarly if this type of reactants is there for us and we just want to substitute this bromine with alcohol, what would happen is, first bromine would get out of the reaction medium, so we would get this carbocation. Again, this carbocation is 2 degree carbocation. To make it stable, we just rearrange this thing, right? So what would happen after that? So after getting rearranged, we would get another carbocation which is a 3 degree carbocation, right? Now if this thing reacts with OH minus is there in the reaction medium, so what would happen is OH minus would get attracted to it and we would get some products like this. So this product we get via methyl shift. As you can see, there is a methyl group which is getting shifted, right? So these are the two types of rearrangements: methyl shift and hydrogen shift. So the reactivity order for SN1 type mechanism is 3 degree, 2 degree, 1 degree and methyl halide. As you can see, in SN1 mechanism, carbocation is formed and this is the order of the stability of carbocation. So for that reason, this is the same order as for the reactivity of SN1 mechanism. Now, and some extra points are there to be added. Allylic and benzylic halides on SN1. So allylic and benzylic halides are very much susceptible towards SN1 mechanism. Apart from this 3 degree alkyl halides, all allylic and benzylic halides are also very much susceptible towards SN1 mechanism. So as you can see, allylic and benzylic carbocations being very much stable, they undergo SN1 mechanism. How? As you can see, this is an allylic carbocation, right? So as you can see, this allylic carbocation can undergo the resonance and it would get a stabilization by this. So although this carbocation being a 1 degree carbocation, this is exceptionally stable due to resonance. So that's why allylic carbocation undergoes SN1 mechanism. Apart from that, there is another example. Right here also you can see this is also 1 degree carbocation. But this is also exceptionally stable because of this benzylic. This is benzylic carbocation. So as this benzene ring undergo the resonance configuration, as you can see, I have shown you all the resonating configuration. So you have read it all in class 11, right? The resonating structure. So for that reason, I'm not explaining all these things to you. So as you can see, there are so many equivalent resonating structure for benzylic carbocation. So for that reason, SN1 reaction, benzylic and allylic carbocations, although being 1 degree, are exceptionally susceptible. Okay, so that's all for today. And the next video we are going to concentrate on the elimination reaction.